Hi Rocketeers, I'm Charlie Garcia, and in this episode we're going to be talking about aerospikes. Aerospike projects are always over budget and behind schedule, and we've just never seen one live up to its potential. I won't be going that in-depth into the pros and cons of aerospike engines. If you want that, you should check out Everyday Astronaut's video here for a mini documentary on the pros and cons of aerospike engines. But what we will be talking about is how to design an aerospike nozzle. Now, I'm not talking about like plugging this into software, letting the computer design a rocket nozzle for us. No, I'm going to show you the equations and the math you do out by hand in order to design a rocket nozzle. And actually, this technique is very similar to what you would do for a bell nozzle, if a little bit simpler for an aerospike engine. Yes, that's right, aerospike nozzles are actually much easier to design by hand than bell nozzles. So in order for this episode to make sense for you, I'm going to assume that you've at least seen the previous episode I did on the nozzle and how nozzles work for liquid rocket engines. The technique we're going to be doing today is called method of characteristics. It's actually the same technique you use to design bell nozzles, but if we were designing a bell nozzle, the math is actually considerably more complex. You have to go through a lot more iterations of it to get it to work well. To start off with, we are going to define a couple of things here. So, the first thing we're going to talk about is the Prantle Meyer function. Now, Prantle Meyer is a equation that defines the maximum angle that supersonic flow can turn isentropically. So breaking that down, supersonic. Starting with supersonic is important because in gas dynamics, a nozzle can follow two branches, with wildly different results depending on if the gas is supersonic or subsonic. Luckily, we all know how throats work, so if we make the throat small enough to choke the flow, we'll guarantee we're getting supersonic flow to plug into the rest of the nozzle. Next, we need to know what isentropically means. So isentropically means constant enthalpy. Isentropically means constant entropy. Entropy is defined by the second law of thermodynamics, but for this explanation, all you really need to know is that if a process can be run in reverse, it is isentropic, i.e., if you can do the process in both directions without wasting any energy, it's isentropic. A good nozzle is isentropic, or at least close enough to it that we can get away with calling it isentropic. Gas expanding smoothly is technically an isentropic process, i.e. all the thermal energy you convert into kinetic energy in the nozzle can be converted back to thermal energy if you just compress the gas back by decreasing the area of the nozzle again. Now, supersonic flow complicates this because supersonic fluids can have shock waves, and shock waves break the isentropic assumption, because in shock waves you lose energy to irreversible processes. So shock waves do really weird things to your flow and ruin your isentropic flow assumptions. Shock waves typically form near corners in nozzles, also at sharp points. If you think about an aircraft or a rocket flying supersonically, you get shock waves at the leading point of the vehicle and the trailing edge, and also like at the roots of the wings and the tips of the wings and things like that. So shock waves, not good, but we kind of have to deal with them as a fact of life of working with supersonic flow. So just to kind of bring it all home here, the Prantle Meyer function is telling you exactly how much you can turn the gas to expand it without getting shock waves that'll waste your energy. And that's important to know because in a rocket nozzle you want to expand the flow as quickly as possible so that your nozzle is small and light, but also no faster than possible, otherwise you'd be wasting energy. So just really quick here, we're going to go ahead and write down the Prantle Meyer equation. It's actually pretty simple. So it's the expansion angle is going to be the square root of gamma plus 1 all over gamma minus 1, tan, or that's an arctan, of the square root of gamma minus 1 over gamma plus 1 times the quantity m squared minus 1, close the quantity, close that arctan, minus another arctan of square root of Mach squared minus 1. Okay, so breaking that down real quick, this gamma is the specific heat ratio, and this is a gas property, and it's typically about 1.2 for rocket exhaust. So the next thing we're looking at here, actually the only other thing we're looking at here is the Mach number, where m equals the Mach number. And just some kind of important trends here. The way Mach behaves in this equation, the faster the flow is, the less you can turn it before you have problems. So what you're really saying here is that slow-moving flow, you can turn it around a tight corner. Fast-moving flow, if you try and take it around a tight corner, you're going to have problems. All right, the next thing I want to talk about is called a simple region. So a simple region, you can imagine, is like a tube that we have gas flowing down at least supersonic speeds. So we'll say Mach equals 1.1 just for discussion purposes. And let's go around this corner right here. And we've already known when we were discussing the Prantle Meyer function that we're going to change the angle of the flow so it'll expand and we will see an increase in its velocity. But the question is, what is the behavior of this? And in a simple region, it turns out that it's relatively simple to calculate how the flow behaves as it transitions through this region. So the last thing we want to get out of the way before we start talking about how to design this is called a Mach wave. So a Mach wave is kind of what's going on here in this expansion fan. So we call this kind of set of lines an expansion fan, and it is the set of Mach waves, or characteristic lines, that describe how the flow turns. So if we just draw out what the expansion fan is here, that's what the expansion fan looks like, kind of as the flow turns to fill out kind of this new region. So Mach waves are how pressure changes propagate in supersonic fluids. So they're always going downstream, and the Mach waves are kind of what eventually form shock waves. So if a bunch of these Mach waves bunch up, you'll get a shock wave. Now remember, we were talking about how shock waves are problems because shock waves are not isentropic. Shock waves, when you go over a shock wave, you lose energy to irreversible processes. So we really don't want to form shock waves, but we do need Mach waves because Mach waves are how we're going to lower the pressure, expand the gas, and accelerate it up to high velocities to get us the thrust we're looking for. Quick here, draw the spike and the shroud geometry. So the spike is this thing here in the middle, and this shroud is this assembly off to the side that forms the lip of the chamber. So shroud, and then this is the spike. So then this in here is the combustion chamber, and then this right here is going to be our throat plane. So the throat plane is the smallest constriction, so that's where the gas is going to go supersonic. And then as we were discussing earlier, we will have our expansion fan. We'll make that a little more obvious. Like that. And because these are characteristic lines along the Mach waves, we can calculate what the properties of the gas is along all of those. So we didn't know exactly what the shape of any of this was to start with, but by knowing that it has this geometry, what we can do is we can calculate where these Mach lines will intercept the shroud contour, and that'll tell us what the spike contour needs to be, knowing that the expansion fan originates at the corner of the shroud and the lines propagate out to the spike. So just to kind of be somewhat rigorous about this, so we kind of guesstimated what the spike is going to look like, and we're going to check all this here at the end. The center portion right here is the spike, and then this little lip right here is the shroud, and that's what makes the throat. This is a full-length toroidal aerospike. That means that it's radially symmetric. And the spike is not truncated at the end. It actually is easier to design a linear aerospike. You get to drop a couple of terms in the differential equations sooner. But just for giggles here, this is a toroidal aerospike. I already had all the math set up to do it. Alright, so remember we were talking about how the gas goes supersonic at the throat, so Mach 1 at the throat right here. And then normally what you would do, if you were designing a bell nozzle, is you would pick what Mach number you wanted the exit to be at, and then you would figure out, and then you would space these lines equidistantly to reach that Mach number. So like let's say you wanted to draw 10 lines, you go from Mach 1 to Mach 5, then you have a line every 0.4 Mach, because you can figure out what the area needs to be to draw that line to. But we aren't going to do that because one of the primary features of the aerospike is that it's optimally adjusted. So these lines are actually fixed here, but what changes is where the gas leaves the spike based on the back pressure, right? So there's air all around here that's pushing back on the nozzle. And as you go towards space, the ambient air decreases in magnitude, the pressure decreases in magnitude, and you get the flow traveling out farther away from the spike sooner, so it leaves the spike at a larger effective area, increasing its velocity. So we've got a lot of concepts thrown out on the board here, so let's work through and figure out how we do this. So the question is, how long do these Mach lines need to be, and where do they intercept the spike profile? So at any point along the aerospike, if the gas were to leave the nozzle there, it would have some pressure based upon how much it had expanded up to that point. And this pressure ratio can be plugged into the isentropic flow relations to find out what the Mach number would be. Alright, so now looking at our picture, we can find the throat plane. This is the area where the cross-section is the lowest, and therefore the gas will reach Mach 1. We'll assume that we picked this earlier and that we got the right size for the gas to go Mach 1 at the throat. So then, if you notice, right here at this edge of the shroud, we get something that looks a lot like a simple region with an expansion fan, which we already talked about earlier, so we can use all of those analysis tools to help design this. So what our plan is here is we're going to draw in a lot of these Mach lines. We're going to find out where they hit the spike using some trigonometry, and then if we draw in enough of those and we get enough points, we'll be able to tell what the entire profile of the spike is just by connecting the dots to find the final spike profile. So now I've left the hard question for last, and the hard question is, of course, how long are these Mach lines and where do they hit the spike? And this is where all the math happens. So if at any point along the aerospike the gas were to leave the nozzle, it would have some pressure based on the Mach number it had before it left the nozzle, based on how expanded it was. And this pressure relationship can be plugged in, and this Mach number can be plugged in to the isentropic flow relationships to figure out what the pressure is. Now, the atmosphere is pushing back with some pressure, and so as the flow travels along the aerospike, its pressure decreases, and eventually at some point in time it matches the pressure of the atmosphere around it, and it then departs the nozzle. So the other important thing here is that there's no rule that the flow has to leave in a straight downwards direction. It could leave this way, it could leave this way, it could leave that way, which would be bad. We don't want that because of something called cosine losses. So if the flow leaves with a direction like this, it'll impart a force like this. So this is our velocity, this is our force, and then if you draw out the triangle, right, any velocity you have in this direction, this is the angle it departs at, this is the sine of that angle, and so then your force is now decreased. Your force that you get is only the cosine of that angle upwards on your rocket. So this is a problem. This is called cosine losses, and they're not great. So the way you avoid cosine losses is the velocity of the gas when it leaves the spike needs to be in a straight downwards direction. And conveniently, we can actually figure this out because we know the Mach number. We know we want all the velocity to be directed in axial direction at all pressures, otherwise we're wasting thrust pushing on our spike when instead we want to be pushing on a rocket. And then we can use trigonometry to figure out what expansion angle from the Prantle Meyer function we talked about earlier gives us that, what angle gives us that, so that we can have the flow leave the spike in a perfectly axial direction. So we have to do the math now. This is the fun part. So let me start writing, and I'll be back with you in just 1 second. Alright, so we're back at it, and what we got is pretty simple. So we've got the equations I was talking about to find what the pressure is based on the Mach number. We've got inverse of the equation here, so we can find the Mach number from the pressure ratio. And then we have this relationship here, which is the set of equations we're going to use to actually find what this spike angle is going to be at every given point. So that's new. That's the Prantle Meyer turning angle we talked about earlier, and that's deltec. That's the shroud angle that we were talking about. So what this really says is that, remember how we were talking about at low Mach numbers, the flow can turn a lot. And at high Mach numbers, the flow can't turn very much. So what that means is that here, where the flow is slow, it can turn and go straight like that. But here, where the Mach number is very high, it can only turn a little bit to depart the shroud at 90 degrees. And so 90 degrees we've just eventually defined as straight down. We're saying that the flow essentially has to make a right angle turn from where it leaves here to where we want it to be. So the flow is coming in perpendicular to the direction of travel of the vehicle, and we want the thrust to be 90 degrees offset from that vector. So this is all the math we need here, and what this is going to give us is essentially what we're going to do is we're going to calculate this for each one of these characteristic lines This will tell us what the angle of the spike is at that point where that characteristic line intersects. So what we would say here is that there is some characteristic line here, where let's say that along this is the Mach 1.4 characteristic line. We would plug Mach equals 1.4 into here, solve for the pressure relationship, and plug that into Prantle Meyer and get the Prantle Meyer angle, and that'll tell us that at this point in the slope, at this point in the spike, what the slope of the spike needs to be. So now we have to figure out how to go from a list of slope angles to the spike profile, which is going to be even more trigonometry. Alright, this video is getting a little long, so let's wrap it up. So what we've got here is we've got the center line of our toroidal aerospike that forms some shape contour like that, that has some shroud, that forms some throat plane. And we've got our simple region of expansion fans that come out from the end of our shroud, like this, where each of these lines represents a Mach number. And we're going to pick a Mach number for the total length of the spike. So for example, in this case we could say like Mach equals 2.5, which would be a fairly typical Mach number for a rocket engine. So then we can just go ahead and say that like this is the Mach equals 1.1 line, this is the Mach equals, well, we'll call that the Mach equals 1.75 line, and then this is the Mach equals 2.5 line. And so what that means is that we will, by solving this setup we've got here, have three spikes, three positions on the surface of our spike. Because we'll be able to solve for the position of the length and the position of this point here, and the position of this point here, and the position of this point here. So then you can imagine how if we extrapolate this to if we were designing a real aerospike, we would solve this, say, 100 times for, a set of Mach numbers in between, 1.0 and whatever our desired exit Mach number is. That needs an E. And that would let us solve for the entire profile of our spike. So now that we've got this setup, now we need to talk about how we solve for the properties of these expansion lines. Alright, so we've got these three Mach lines here, and we need to solve for the Prantle Meyer angle at each of these lines, which we can do because we have the Mach number, which we've kind of chosen a priori, right? So we've plugged in the Mach numbers, and now we're going to solve for the Prantle Meyer angles. So we've got the Prantle Meyer for Mach 1.1, Prantle Meyer angle for 1.75, and then the Prantle Meyer angle for 2.5. And these equal I'm not doing out the math by hand. I think the equations presented earlier make it, I hate to say it, but trivial to do. So just write a script or get your calculator set up and plug in Mach equals 1.1, 1.75, and 2.5 into that with a gamma of 1.2, and you get 1.5 degrees, 22.5 degrees, and 48.5 degrees, roughly. So now that we've got that, those are the Prantle Meyer angles along each of those Mach lines. So now that we have that solved for, we need to solve for the Mach angle at each of those positions. So that's going to be relatively straightforward. That's going to be represented by this mu character, and so we'll have that once again for 1.1, mu for 1.75, and for 2.5. Alright, so just real quick, what does Mach angle represent? Mach angle is the angle between the flow velocity and the local Mach line when the flow is expanded to the Mach number for that particular Mach line. So if we're looking at the case of 1.75, the flow will be moving along the spike, and so the question is, what is the angle, right? So if you've got the spike here and a Mach line coming in like this, and the flow angle is like this, the question is, what is that angle there? Just to zoom in on that. And the calculation for this is also very straightforward. It is that mu of x equals arcsine of 1 over the local Mach number. Alright, so we've gone ahead and computed the Mach angles, and we can use these two pieces of information to begin to describe the rest of the spike geometry. So the first thing we need to understand is that since we have radial symmetry, essentially what we have is we have a frustum. That's the name for this kind of like truncated cone shape. And we know some things about this frustum, right? So this frustum is composed of these Mach lines, where the area of this outside of the frustum corresponds to the expansion area we showed earlier for a given Mach number. And additionally, we know what the angle, if there's like a line there, we know what that angle is there, because that's going to be the angle, because the spike, this inside circle here, is where this frustum shape intersects the spike. And because we know that angle right there from calculating the Mach angle, that will let us calculate what the area of the frustum is, and then that'll let us know by either knowing what the diameter of the spike is or the height of the spike is, we can then learn everything else about the frustum's geometry, right? So it'll give us two tightly coupled parameters, the radius and the height of the frustum. And so then all we have to calculate is we just have to pick either the radius or the height, which we could either do by assuming a truncated aerospike and then setting, you know, the final frustum dimension at 2.5 to have the correct radius, or we could say that at Mach 2.5 the spike is a perfect point, and then we would know that that radius was 0 and we could set the height. And so that then fixes all the information that we need to know in order to solve for the location with just a little bit more math. So I'll get to that and be right back. Alright, so we're almost there. So we know everything we need to know to solve for the contour of the spike, except we still have a floating relationship between the radius of the spike and the height of the spike, and we don't have a solution for that yet. So there's a variety of ways we could do this, but aside from guessing and checking, the right way to do this is going to be to solve for the mass flux through the throat, which is also going to be equal to the mass flux through the frustum defined by this Mach 2.5 line here. Because we know that conservation of mass says that all the mass going through the throat needs to be leaving the nozzle, and since we've decided that the nozzle ends at Mach 2.5, the frustum defined by Mach 2.5 must contain all of that conserved mass flow. The derivation of this equation is incredibly messy, so I'm just going to go ahead and write it out here and just know that it's derived from essentially saying that m dot t equals m dot e, that is mass at the throat equals mass flow at the exit, and that you're using some gas relationships where the rho of the gas of the throat, the velocity of the gas of the throat, and the area of the throat is equal to the rho of the gas at the exit, the velocity of the gas at the exit, and the area of the exit. We have the area at the exit calculated here, and we can calculate the velocity of the gas at the exit by knowing we picked Mach 2.5, and then finding the velocity is just 2.5 times square root gamma RT. And then we know we can calculate the density of the gas from isentropic flow relationships, which is just some more math to go run down. And then, when all of that is said and done, you get to this horrible expression, which I'm just going to write out here. And this holds true on any of these frustums, so you can set this no matter what your no matter what your Mach exit is, you can use this equation. Alright, goodness gracious, so we've got that all written out. So this is the radius at x as pertaining to the radius at the exit of the nozzle is defined by this function here, where this is all under the square root, and I just had to continue this on the second line. And then the h can be obtained from the height at that position of the nozzle can be obtained by this function here, where 0 is defined at the throat of the spike. Yeah, so that right there is sufficient to define the entire geometry of the spike. And then if you're curious what the gas properties are at any position along the spike, essentially you find the area of the frustum from this equation here defined by a line going to it. That gives you a Mach number, and then you can throw that Mach number into the isentropic flow equations and solve for things like the temperature, the density, or the velocity. So really, that's all you need to do to design your aerospike. And this has given us a set of 3 points, so just to kind of finish off. So we've got our shroud here, and we've got kind of our spike geometry here, where this is 0, and then this center line here is also 0, and we have 3 points for Mach 1.1, 1.75, and 2.5, and we have these positions now in 2D space, and then to derive our 3D nozzle geometry, all you have to do is rotate it. And let me just go ahead and get those all set up. Alright, so I've gone ahead and computed the radius as it pertains to the initial radius for the following parameters. For Mach equals 1.1, the spike is, 98% of its full diameter. For 1.75, it's 41% of its full diameter, and for Mach 2.5, it's about 19% of its full diameter. You need to make some assumptions to plug into this in order to get your starting parameters. So I threw in the parameters for the J2X engine, or rather the J2T engine as it was being designed in the 1960s. So that's a PC of about 5 megapascals, a TC of about 3,450 Kelvin, with a relatively low molecular mass of about 12 grams per mole, and a gamma of 1.2. And an ultimate expansion ratio, if you take this all the way out to an infinitely fine spike, of 57.4 would be your expansion ratio. So that does it for designing an aerospike. Alright, that does it for episode 9 of Liquid Rocket Engines. Just for the record, I'm not planning on putting an aerospike engine on my rocket. It doesn't make a lot of sense for the design that I've put together, but I did a lot of work for this video back a couple of months ago, and I just thought I'd put the effort in now to finish it up because you guys might enjoy seeing how aerospike nozzles are designed. Bell nozzles are designed using the same technique, using simple regions and Mach lines, but then you also have complex regions as as the Mach waves interact with each other near the center of the nozzle. So it requires an iterative solver, and it's absolutely tedious and horrible to do by hand. So we're not going to do it for bell nozzles. But this is how my computer simulations would solve for the parameters of a bell nozzle that I will be using on my liquid rocket engine. Thank you so much for taking the time to watch this video. Hopefully it was at least a little bit interesting. I tried to keep the math tame and accessible to everyone, but it was still going to be kind of math heavy just by design. If you have any questions, ask them down below. If you catch any mistakes I made in the process, definitely leave those down below so I can get them fixed. But I'm relatively confident that this produced a good result. Thank you so much once again for watching. If you've enjoyed this video and you'd like to support my work, you can join my Patreon down in the description below, or you can just watch this video with ad block turned off. Either way, I will see you on the next episode of Liquid Rocket Engines with hopefully some more hardware showing up. As always, good luck, Godspeed, live long and prosper, don't shake anybody's hands. Have a nice day.